Good morning, all. So, in the last class, we have discussed about the induration process. We have discussed about induration process through stride plate as well as grate kiln technology. So today, um, in this particular section, we will discuss about what are the various changes which occurs inside the pellet during this induration process. So as we have seen, there are three different stages are there in the induration process. One is the drying, and then the preheating, and then firing. Of course, finally, there is a cooling process also there. So, uh, whatever the green pellets which are formed on the disc pelletizer, so these green pellets basically they travel through the conveyor belt and then it undergoes screening by double deck screening system. And once the screening has done, the pellets of size approximately around 8 to 16 they are allowed to pass through the conveyor belt into the induration process. So as we discussed in the previous classes regarding the induration process, where you have the drying zone consisting of two parts. One is the updraft drying zone, other one is the downdraft drying zone. And you have preheating zone, zone 1, preheating zone 2, and then you have firing and after firing. Then we have cooling zones also. So we will see what is actually happening in at every stage of this preheating process. So in the updraft drying zone, you can see here the chemistry of the green pellets which are coming from the fertilizer, and these green pellets are subjected to the induration process. So the first stage of induration is the drying zone. The two, it is the updraft drying zone. So in this zone, basically, water which is present in the pellets, moisture content which is present in the pellets are usually get removed. So nearly approximately around 15% of the water will get evaporated by consuming the thermal energy from the hot gases. So you can say there is the only difference in the abrupt drying zone. The only difference when the pellets will undergo is the removal of the moisture content. Okay, so here you have in the green pellets of around approximately 8% is there. Then when it is subjected to the abrupt drying zone, its water content will be reduced to 6.8. That is the only difference what you can observe in the abrupt drying zone. Rest all parameters are constant, the same. And then the pellets are moved to the downdraft drying zone, where here also the only thing what we see the great difference is the removal of the moisture. So only drying of moisture nearly 35% by consuming 48% of thermal energy will take place. So there is no chemical reactions occurs in the drying zone. So here also again you can see the water content. So initially, as you can see here in this particular picture, the water content is around 8%. It is reduced to 6.8. Now this composition pellet will move further to the downdraft drying zone. So in that case, the input chemistry will be this thing, and the output chemistry, you can see input chemistry have having a water percentage of 6.8%, and that 6.8% will be undergoing to downdraft drying zone, and now it is reduced to 4.4%. Okay, so in the updraft drying zone and downdraft drying zone, The only difference is that the pellets which are in the upper drying zone, the pellets which are in the lowermost layer will get dried off first, and it gains strength. And in the downdraft drying zone, topmost layer of the pellets will also expose to the temperatures, and the drying will be taking place. In this way, once the pellets have moved from the drying zone, a good amount of moisture content is removed in both surface as from the top as well as from the bottom. Now, once the pellets are moving to the preheating zone, so here the temperatures are slightly getting increased, and it will be approximately around 800 degrees centigrade, where the calcination basically takes place. That is, CSU, the dissociation and all takes place. So most of the chemically bonded water starts drying away. So you can keenly observe what are the various changes which is taking place in the pellets. That is your initial, you can see in the previous it is this 4.4 water content. Once the pellets has reached to the downdraft drying zone, now the water content will be completely get removed once it is subjected to the preheating zone. That you can see here. From 4.4, the water content is reduced to 0. So means complete moisture content is removed once the pellets are moved to the preheating zone. And as I told you, there is a dissociation of limestone basically takes place, which is the formation of CaO and CO2. So that you can clearly see here. The limestone content initially it is 1.6, so after dissociation it is reduced to 1.1. Then carbon is 1%. Then you have the as it is dissociated into CaO and CO2, so there is a possibility of CO2 to come into existence here, because initially there is no CaO or CO2 here. It is only the limestone. So after dissociation, you can see the certain amount of these two products in the pellet. And you have, once it is moved to the firing and after firing zone, the calcination reactions completely ends, and there is a slight possibility that because of the high temperatures, there is a possibility that, because when it reaches to the firing and after firing means almost it is around 1000 to 1100 degrees centigrade, that is the maximum temperature. So here there is a slight change in the phases. That is there's a transformation of hematite to magnetite, or may little bit have oostite, may also can be takes place. Can see in the pellet. So as I told you that the calcination reaction ends in this particular zone. So that you clearly observe that here initially it is limestone is 1.1. That is what we have seen here. The limestone is 1.1. Now when it reaches to the firing and after firing zone, the limestone is completely 0. Means it is completely dissociated into CaO and CO2. There is no further limestone is present. But only thing is the burnt lime is present and the CO2 is present. You can also see CO2 content is also increased. And as I told you that there is a slight change in the phases. It may change from hematite to magnetite, or may little bit oostite also. So that's why you can also see initially there is no magnetite, but yeah, there is a slight formation of magnetite is observed in the firing and after firing zone. So hematite ore grains lie side by side without any bond till 1200 degrees centigrade. Above 1300, first crystal bridges forms, and longer induration time is required for sufficient bridge formation. So at high temperatures, hematite start to dissociate into magnetite, resulting in weakening of the pellet. So we should not go for very high temperatures. And the cooling zone, the ambient air cools the pellet to 100 degrees centigrade, because this is what happens in the annular cooling zone, where the suction basically takes place. We supply the air from the bottom, and from the top there is a suction basically takes place, and the temperature of the pellet can be dropped down to around approximately 100 degrees centigrade. So after cooling, the discharge pellets will again travel on a conveyor belt for the screening purpose, where it will be screened between 8 to 16 mm, and undersize and oversize will again sent to the stockyard to the conveyors, and they can be used as a hearth layer. Here you can see the final composition of pellets. You have hematite around 82.2%, manganese 1% at EVO at least. And the chemistry of the pellets, you can see it can be around FeNF, SiO2, Al2, the CaO, MgO, and all. This is the final composition of the pellet. So once the induration process has completed, now the pellets are ready for the charging, the fired pellets. But before we charge any raw material in the blast furnace, just in the previous model we have seen that the coke, whatever it is prepared, either by any of the technique, by slot kind of thing, or by non-recovery coke ovens. Before we subject this coke as a fuel into the blast furnace, we have done some things to check the feasibility of this coke to sustain at blast furnace environments. Similarly, the agglomerates, whether it is sinter or pellet, whatever it may be, before we subject these iron bearing material into the blast furnace, we have to check the feasibility of sustainability of these agglomerates inside the blast furnace without generating fines. So we have some tests which we need to perform for these agglomerates, both for sinters as well as pellets. Once the pellets or sinters, once it is undergone these tests, and if it is sustained, then we can say these agglomerates are having good quality, so we can utilize this in the blast furnace as iron bearing material. So there are some high temperature testings are there, and as well as room temperature testings are also there, which we need to suppose to perform for these agglomerates. Room temperature physical tests, if you see, that is, one is a drop test, and then a porosity test, then shatter, or you can say the tumbler test, then CCS, that's cold compression strength test. These are the room temperature tests which we perform for the agglomerate. So see one by one. So the drop test, basically we do it for the green pellets to check its strength, drop strength, so that during its transportation it should not get fragile. So here it is a very simple test. Whatever the green pellets which are obtained from the disc pelletizer, so these green pellets have to be dropped from a height of around 46 centimeters on a 10 mm thick plate, so that it has to be dropped till it gets fracture. So that will give the drop strength. So we have to drop a pellet from a height of 46 centimeter on a 10 mm thick plate, and we have to repeat this thing till the pellet get completely cracked. So the average value of at least 10 pellets we should take it. The average value of this will be taken into the consideration. So you can see that in commercial plants, the drop number for different ores, which is the hematite, it should be minimum of 5, magnetite is 7, limonite is 7. So this is a drop number. So higher the drop number means higher it is having a higher spin strength. This is very good for transportation of the pellets. Then the next thing is the porosity. So this is basically works on Archimedes principle. So the porosity of the pellets are very important, because especially if you see the sinters as well as pellets, the agglomerates. Sinters we can see the porosity with the naked eye, but the pellets it is a micropores, we cannot see with our naked eye. And this is because of this property only we are actually using 85% of the agglomerates in the blast furnace, so that the porosity of these products help in enhancing the rate of reduction reactions inside the blast furnace. So the procedure for this is very simple. That the porosity of the pellets is usually measured by using kerosene. So you just drop these pellets inside the kerosene and keep it for some time, and then remove it, and then you can check it what is the true density and what is the apparent density. The difference of true density by apparent density by 2 density into 100, you can give the porosity. And then we have a shatter test. This can be done for both sinters as well as for the pellets. So here this is used to determine the strength of the pellets. A 20 kg of sample of plus 10 mm size is dropped from a standard height of 2 meter on a 10 mm thick plate for 4 times. So the amount of metal passed through certain sieve is indicated as the shatter index. So this will determine the stability of the agglomerates. Especially it gives the impact strength. The shatter index will give the impact strength for sinter and pellet. So for sinter, this is the formula which we need to use. That is the weight of minus 5 mm fraction in kg by initial weight of the sample. So whatever the initial sample you have taken is 20 kg. So you have to drop it from 2 meter height for 4 times. And then the top product, whatever it is there, that you have to sieve it using 5 mm screen. And the weight of minus 5 mm fraction that you need to take into consideration. And we need to weigh that quantity, and then that divided by initial weight of the sample. That is 20 kg into 100. That will give the shatter index for the sinter. Similarly, for pellet, if you see, it is the same procedure, but the only thing is that we need to take the weight of the sample of minus 100 ms size by initial weight of the sample into 100. This will give the shatter index for the pellets. For alternative, you can see that is the tumbler drum or tumbler index test, where it will give an idea about impact and abrasion resistance of the pellets. So this is the phenomena basically which happens inside the blast furnace. When you are charging the raw material, any raw material, whether it is coke or the iron bearing material. Even in fact, for coke also we do these two testings. Impact and abrasion is mica index. So for pellets, we use the tumbler drum, and we do the tumbler index test and abrasion index test also, which will determine the impact and abrasion resistance of the pellet. Because this is very important, because if the raw material having low impact strength and low abrasion resistance, then generation of fines will be more. That leads to the loss in the permeability of the bed inside the blast furnace. So this will hamper the working conditions of the blast furnace. The blast furnace may get hanged. So the procedure for this particular experiment is initially we need to take 15 kg of pellets of size above 8 mm, and that is to be introduced into the drum of dimensions 1 meter diameter and 0.5 meter length. These are standard dimensions of the tumbler drum, and this drum is allowed to rotate for 8 minutes at an RPM of 25. That is 25 into 8. That is 800 revolutions will taking place. And after that, you need to collect the sample from the drum, and we need to submit the sieving operation. So here we need to use 6.3 mm sieve, and we can obtain the tumbler index as well as operation index. So where you can see this is a formula, that is for tumbler index T is equal to m1 by m into 100, and operation that is m minus m1 plus m2 by m into 100. The capital M is nothing but mass of the sample, that is initial sample, and m1 is the mass of the sample retained on 6.3 mm. Okay, so this will give mass of the sample retained on 6.3 mm. So this will give the impact. Okay, so mass of the sample retained on 6.3 mm divided by the initial sample, that is 50 kg. And M2 is nothing but the mass of the sample passing to 6.3 mm and retained on 500 micron sieve after the test. So this is the formula which we need to use for the aberration index. So for good pellets, respective percentage should be of around 85 to 95. And 3 to 7. That means the tumbler index should be of around 85 to 95, and aberration index should be of 3 to 7 per pellet. Whereas for sinters, it should be of the tumbler index should be of 60 to 80, and the aberration should be of 5 to 10%. And for ore, that is for the lumps, it should be of around the tumbler index should be of around 60 to 95, and the aberration should be of 2 to 25. So whatever the agglomerates which we are preparing by sintering process or by the pelletization process, so these should have the impact and aberration resistances of a particular range. This range, then you can say that these kind of agglomerates are feasible to use as a iron bearing material or as a part of a charge inside the blast furnace. Then the crushing strength, yeah. So the pellets, whatever are prepared, once we charge inside the blast furnace, so usually the entire burden will be settled in the form of layer by layer inside the blast furnace. So the pellets should sustain the load above it. So to find that, we need to do the crushing strength. So a minimum of around 2000 Newton per pellet, that should be the strength for the fired pellet should be. So in order to determine the crushing strength, at least we should take 10 pellets from a lot, and we need to subject those pellets between these two jaws, upper jaw and lower jaw. One is fixed, other one is the mobile condition. So we need to allow Once we have kept this pellet in between these two jars, we need to allow the jar to uh, mostly the upper jaw will be fixed and lower jaw will be in the moving condition. So it is allowed to start once these two jaws are come in contact with the surface of the pellet, then the load start applying on it, and it is absorbed on this digital screen. There are some manual and there are some automatical equipments are there for performing this particular experiment. So like that, we should take the average of our average crushing strength of 10 pellet taken from the same lot, and that will give the average strength of average uh, crushing strength of pellets. Then the reducibility. This is this is also very important. It is high temperature uh, test. So the reducibility is a measure of oxygen removal rate from iron oxide by reducing gases, either CO or H2. The reducibility can be measured by degree of reduction with respect to the time. So in this test, we need to take 500 grams of a sample of size 10 to 12.5 mm, and these are introduced in a drum of dia 75 mm and 200 mm in length. And the sample is exposed to reduction conditions by supplying 40% of CO gas with 60% of N2, with a flow rate of 50 liters per minute, at temperature up to 9 degrees centigrade, for a duration of around approximately 4 hours. Then the sample is collected and weight loss method is generally used to determine the degree of reduction. So you can see from this particular formula, that is W1 minus W2 by W naught pi into 100 is equal to delta W naught by delta W naught of I into 100, where Wi is the initial weight of the sample before reduction, and W2 is the final weight of the sample after reduction, and delta W naught is the weight loss due to oxygen loss during reduction, and this is W naught of I, that is total removal oxygen present in the sample. So to calculate what is the total removal of oxygen present in the sample, this is the formula again. So from this we can find it out what is the degree of reduction. So this is very important, because if the degree of reduction is good, then the reduction rate should be high. Of course, for that again, porosity is also very important. Then decryptation, yeah, this is also very important, especially during the charging process of raw material. Uh, when iron bearing material are suddenly exposed to the off gases at the stock level during charging process, there is a possibility that the crack formation may take place due to thermal shocks, because we are not doing any preheating of any of the charged material. We are taking the raw materials from the room temperature and simply charging into the blast furnace. So the off gas temperature will be approximately around 150 to 200 degrees centigrade of the blast furnace. So once uh, the raw material, especially pellets and all, once they exposed to the high temperatures from room temperature, so there is a possibility that the crack formations may take place because of thermal shocks. So that will again may tend to formation of fines, generation of fines inside the blast furnace at any point of time. So to determine this degradation process, so pellets should have sustainability for this kind of problem. So to determine this, we are taking again 500 grams of sample of 20 to 40 mm size, we get to a temperature of 400 degrees centigrade. and retained for 30 minutes under flow rate of 5,000 liter per liter of nitrogen per hour. And the samples are removed and then cooled, and percentage of minus 0.5 mm and minus 5.62 plus 0.5 mm product is determined by CV. So a typical set of results, if you can see, that is hematite. This hematite ore, then the percentage of minus 0.5 mm should be around 1.1, and this should be around 8.9. Then we can say that these iron bearing materials have good resistance to degradation. Then we have a low temperature breakdown test. So again, here also we subject this, especially for pellets. Sufficient mechanical strength of fired pellets is an important prerequisite to their optimum behavior during transportation reduction. So during reduction, there is a structural changes occurs inside the pellet. So these changes occurs at a relative low temperature, around 500 to 600 degrees centigrade, resulting in a certain degradation and thus impairing the gas permeability of the pellet charge. So LTB takes place at the upper zone of the blast furnace. So this is basically carried out in a rotary kiln. This test. So 500 grams of sample of 10 to 12.5 mm size is green pellets we are taking, and reducing, and we are subjecting to a reducing gas of around 40% CO and 60% N2, the flow rate of 50 liters per minute, and we are maintaining a temperature of around 500 degrees centigrade for 1 hour, and then we cool it to cool in the nitrogen environment. So after the reduction, the material is subjected to rotation at 30 RPM for 300 revolutions in a drum having a dimensions of 130 mm diameter and 200 mm length, 10 minutes. And then the material is screened, and percentage of plus 6.3 mm is called the low temperature breakdown index. So as per the commercial plant data is concerned, the LTP value should be minimum of percentage of 80% should be there. Means the amount of plus 6.3 mm pellets should be of at least 80% after scaling. And then we can say the pellets are having good low temperature breakdown resistance. And we have a swelling test. So especially again, this is for the pellets. So at rising temperatures up to 1000 degrees centigrade, the pellet volume may increase beyond the initial volume. This volume increase is known as swelling. With swelling, the strength may diminish so that the pellet may even crumble, whereby the gas permeability is further impaired inside the blast furnace. So according to the chemical composition of the pellet, they start to deform plastically at a relatively early stage, and that will impair the gas flow. So the purpose of this test is limited to the study of swelling behavior of the pellets. So the procedure for this one is again, we are subjecting to the pellets to a temperature of around 1000 degrees centigrade in an atmosphere of 40% of CO and 60% of N2. And we are allowing these pellets to subject for different temperature, different times. That is 15 minutes, 40 minutes, 70 minutes, and 120 minutes, with a reduction of around 25 to 80% being attained. And the volume of a certain number of pellets is measured before and after the test. And the results in the commercial plants are showing that the swelling index should be, for good quality pellets, swelling index should be less than 20%. And this is the formula which is used to calculate the swelling index. That's V final volume minus initial volume by initial volume into 100. And then we have a reduction degradation index. During the reduction process, the degradation may take place. So lump ores, sinters, and pellet disintegrate into smaller pieces during their downward travel to the blast furnace, owing to the weight of the overlying burden as well as the abrasion and impact between the burden material. It has been found that this tendency gets aggravated when the oxides are in the reduced state. So the reduction of hematite to magnetite occurs in the upper stack at 500 to 600 degrees centigrade, and this is accompanied by the volume expansion even to the extent of 25%. So this results in compressive stresses being developed and contribute significantly to breakdown of the iron oxides. Again, we carry the same kind of experiment where we take 500 grams of sample and reducing atmosphere 20% CO, 20% CO2, and 6% N2. Flow rate is 20 liter per minute. Temperature 500 degrees centigrade. Reduction rate is 1 hour. And we allow again these samples to rotate in the tumbling drum for 30 RPM for 30 minutes. And the samples are screened on 6.3 mm and 3 mm screens. And we should get a low RDI below 28. So these are some of the testings which we basically do for the agglomerates. Advantages of pellets as a burden material.